So I know you're probably itching to get in and start doing hypothesis testing. But before we do that, we've got 2 pages of work here to kind of give you the picture of how we're going to let the technology and use the statistics that the technology gives us to make correct decisions on whether to reject or not reject the null hypothesis. So we got to talk about what is a rare event. You know, what is a rare event? And what makes an event that has you question your basic assumption or the average or percentage that you were given in the problem? Well, this is when a sample has properties that would be very unlikely to occur if the null hypothesis was true. So if I give you a null hypothesis, let me just say something that I'd have no, I'm not sure about this, but let me just throw out a null hypothesis that the average college student equals 20 years old in age. Well, if we get a sample, a representative sample of a college population, and it has properties that would be very unlikely to occur if the 20-year-old average was true, then I might have to question whether or not the 20 years was correct. So what we're about to do is talk about the thing we're going to focus on, which is the p-value. The p-value is the probability of getting the result from the sample. So what this means is that we are going to measure the percent chance of likelihood it would be to actually get the result of what our sample size gave us. So let's say, for example, I get a representative sample, and that representative sample of college students does not have an average of 20. Okay, so let's say it's 21 or 22 or on the younger side, like 19 or 18. Well, if you got an average that was a little bit over 20, like maybe 20 and a half or 21, maybe that was still a pretty high likelihood depending on your sampling technique and how you got things done. But would you find it odd if I got a representative sample and I found the average to be like 28 or 29? Well, that might give me, that would be such a rare event that might have me question whether or not 20 was right in the first place. Now, there's a very good definition of this in your book on page 511 and 512, but I feel like my shortcutting of that definition to kind of give you the gist that if we have found a sample average or sample percentage, and the chance of doing that was incredibly rare, then we might have to forget that the null hypothesis is right. We might have to reject it. So this kind of dichotomy, if you have a big p-value, okay, so if your p-value is 60, 70, 80, 90%, the big value for p, so a big p-value, means that this is a very likely event. So getting an average of 21 instead of 20 could be very likely because your sampling is going to have some fluctuation to it, and getting an average of 21 when you expected an average of 20 is, going to probably be a pretty big p-value. Now, if you have a small percentage value or p-value, this means that what you had was very unlikely And that is your rare event. Okay? That is your rare... Whoops, I wrote RAE. Thinking ahead. This is your rare event. Okay? A rare event is when you have a small p-value, a small percentage value. So if getting that result was incredibly rare, then you're going to have to reject your null hypothesis. So this right here sets up the most important rule in decision making for this entire unit. If your p-value is less than your alpha, if your p-value is less than alpha, then you reject the null hypothesis. If your p-value is greater than alpha, then you do not reject the null hypothesis. And as a reminder, we do not use the word except. Can't use the word except. We're either going to not reject the null hypothesis because we believe it's true, or we reject the null hypothesis because we believe it's false. So reject if you believe it's false. Do not reject if you believe it's true. So alpha, if you remember back from the previous video, was our chance of making a type 1 error. So if our chance of if our chance of getting that rare event was less than the chance of making an error, then we have truly witnessed a rare event, and we better question the null hypothesis. So I want to talk about this problem here to give you kind of an example with a little bit more detail to it. Now, this is not going to be a full hypothesis test because there are some steps that are actually not going to be part of what actually going to be done for us here. So there's a computer that's programmed, or a game, that's programmed to drop a random legendary item in a loot crate 1 in 30 times. Over opening up, and we're going to assume a very large number of dozens of loot crates, you'll notice that, hey, you got a lot of legendary items. Now, you did some calculations, and again, this is more part of the hypothesis test, but let's just kind of get to the very answer here. You calculate the probability, and you find out that the p-value of that event happening, that's you opening up all those boxes and getting more than what you feel is the normal legendary drop, is this P01322. Can you be 95% confident that your legendary item drop rate is the 1/30th? So this means that our null hypothesis and our alternative hypothesis are going to be basically questioning this 1 in 30 drop rate. So our average is either going to be 1/30th, or our average is not going to be 1/30th. Because again, you're just trying to figure out like, is this correct or not correct? Okay? Now, you might decide instead of putting the not equal to, you could decide instead of putting greater than. Because maybe your position is that you want to be like showing that you get more than a 1 in 30 chance. Now you'll notice that we also have a 95% confidence interval here. So this is our CI, confidence interval. That means our alpha is the complement of 95% from 100%. So our alpha is 0.05. We're going to compare our alpha to the p-value. And from up above, we're going to check our p versus alpha. Our p-value was 0.01322. Now our alpha is 0.05. So we have to decide which is bigger. Which is bigger? Is it the 0.01322 or is it the 0.05? Now, some students at this level might still make mistakes by thinking that the longer number is the bigger number. It's easy to kind of maybe look at this as 1,322 and 5,000. Another way to look at it is to move the decimal 2 spaces to the right and say this is 5% and this is 1.3%. 1.3% is smaller than 5%. In this problem, I wanted to basically say, okay, I do not want to make a type 1 error. The alpha tells me my percentage of making a type 1 error, which is 5%. My p-value is less than 5%. So I had less than a 5% chance of me getting all of these legendary items when I opened up all those loot boxes. So since my chance of getting this result was smaller than my chance of making a type 1 error, we will reject the null hypothesis that 1/30th is the correct answer for the null hypothesis. So here's my conclusion. Since the p-value is less than alpha, there is sufficient evidence to reject the null hypothesis. So this gives you a straight example of evaluating p versus alpha. Now, before I end this section here and get through this first part of the video here, I want to give you this clever rhyme. If the p-value is low, let the null go. So letting the null go is another way of saying rejecting. If the p-value is high, then let the null fly. Which means we will keep that, we would let the null stand, we would let it fly, so the null would not be rejected. All right, so the next piece is to now set up all of the parts inside of our hypothesis test. Now I know you're jonesing to get going on these hypothesis tests, but I first want to set up all of the different things that you have to know in your hypothesis test setup. And I'm going to color code these a little bit too. So the z-tests will be colored blue. The t-tests will be colored green. And the z-proportional tests, or the percentage binomial tests, will be red. And I highlighted this a little purple. So when you read the hypothesis test, you're going to look for important pieces of the story problem. I call this step 0 because it's actually not part of the hypothesis test process, but it kind of gets you ready for it. So our z means we are going to look for our mu, our given standard deviation, sample size, the average of our sample, and we should look for the confidence interval, or alpha. If we have one of these two, we can find the other. Now, if you have t, then you're going to have the average, but you will not have the standard deviation. You're going to have the sample, and there you can find your degrees of freedom. You'll have a sample average, and you'll take that sample average data and find your sample average standard deviation. Notice it's given by the capital letter or lowercase letter s instead of the Greek letter lowercase sigma. And then confidence interval and alpha. Now finally, if you have a percentage problem where you have to verify the binomial percentage, you're going to look for your p0. Your p0 or p0 is going to be what your null hypothesis is going to be tested against. You're going to have a sample size. You're going to have a p-hat, and the p-hat may be given and may not be given, but the p-hat is basically your x divided by your n. A lot of times you don't need p-hat because they're just going to tell you how many people succeeded out of a total number here. So just having one or the other is going to be sufficient. And of course, confidence interval and alpha. So after this video is over, we're going to do 2 examples of the Z hypothesis test, 1 sample, 2 examples of the T hypothesis test, 1 example, and 2 examples of this percentage or the proportion test, 1 sample. So what's your first step in hypothesis testing for all 3 types? Well, it's to label your null and alternative hypothesis. Okay, after doing that, your step 2 is going to have a little bit of verification. So we're going to start off with our z-test. If you have, not with the z-test, all of these is going to ask, is your n less than 5% of the population data? So is your sample less than 5% of the entire population that you're trying to survey? And your answer in this case is almost 99.99%, 99.99% yes. You're definitely not using a sample size that would actually encompass the entire population. So this is just a check to make sure that you can use these kind of tests. So yes, the answer for that question is yes. Because there's no way if I gave you like all of the data, we wouldn't, need to run a hypothesis test. We would have all the data. Okay, so if you have a z-test, you're going to be asked, is n greater than or equal to 30? Okay, that's generally a test in the step 2 there. And that should be a yes. And if it's not a yes, then you have to make sure, if not, then is the distribution normal? And most all story problems are going to be asked about that. Is the distribution normal? It'll probably just say it in the story problem. Now the t-value is going to ask, is n less than 30? And there you would say yes. Obviously, if it said if n was greater than 30, you would say no, because your t examples are going to be small. Now, in this case, if yes, check for outliers. Because we can't assume normality if outliers exist. And I will show you in those t example problems that there will be no outliers, so we can continue on with the problem. So what about the percentage problems? Is there a check for this one? And there is. The check is that your n times p times q has to be greater than 10. Okay, and if it is, then good. Assume normality. So you can use the test in the calculator. Assuming normality means that you have a big enough sample that you can assume that it forms a normal curve. But if you can't, then you have to use a binomial distribution. And we use that called binomial CDF. And that's because your probability, your p prime, is going to belong to your binomial distribution with sample size n and success rate p hat. I would say most of the time your n times p times q is going to be greater than 10. And as a reminder, your q is just your q isn't 1 minus q, your q is 1 minus p. Okay, steps 3, 4, and 5. Steps 3, 4, and 5 are true for all hypothesis tests, no matter which kind you do. Step number 3 is to use your calculator to get your test score, and I will show you what that means in the next video, and p-value. And you've already been given an example of what we do with the p-value. You'll compare your p-value to your alpha. Step 4 is to draw the picture. And what's nice is that your calculator gives you a big heads up about this one here. You draw the picture, and then in step 5, you write your conclusion with an inequality. This is something that I'm adding as a criteria to the problem. I want you to state your inequality that gives you your conclusion. And in the next 3 videos, you will see examples of this. And I'm excited to get into these next videos, and I'm thanking you for kind of going through the pre-work that's necessary to do the next 6 examples. But you are going to be so excited to actually tackle some pretty good hypothesis testing problems coming up, and I'm excited to teach them to you. So thank you for watching.